Now that we know how to solve systems of equations, then there are some applications that we need to take another look at. In the past, when you're working on application problems, meaning word problems of course, there were times in certain word problems where you're asked to solve for more than one value. A student is always tempted in that type of situation to want to use more than one variable. It seems natural, if I want you to solve for two things, that you should use two variables. But so far, we've been unable to do this, simply because we did not know how to solve an equation with two variables in it. Well, we still can't get a unique solution to an equation that has two variables in it. But if we know how to do systems of equations, then what we can do, if we have two quantities to solve for, is to try and come up with two equations and use those two equations as a system of equations and come up with a unique solution. So let's look at a few problem types. One problem type would be a geometry problem. In the past, you've worked problems that dealt with, say, complementary angles. Well, complementary angles, by definition, are angles that add up to be 90 degrees. So in a geometry problem now, you can immediately, upon seeing the word or the phrase complementary angles, you can immediately know that one of your equations is probably going to be x plus y equal 90. If you were to see a problem that said something about supplementary angles, then just from seeing that phrase, you know that one of your equations is going to be x plus y equals 180. And of course they will need to supply more information so that you can come up with a second equation, but just the title of the problem in a lot of cases is going to give you one of your formulas. Let's go back and work a complementary angle problem. The problem might read, two angles are complementary. Find the two angles if one is 18 degrees greater than the other. So, complementary gave us one of our equations. Our other equation says one is 18 more than the other. So there is our second equation. We can solve this through substitution. Since I know what y equals, I can take the first equation, pull out the y, plug in what it's equal to, combine like terms, then I'm going to subtract off the 18. So 2x is going to turn out to be a 72. Dividing by 2, x is a 36. And we have two ways to find the other one. In the second formula, it says that if I add an 18 to the 36, then I can find my other angle. So your two angles are 36 and 54. So just the fact that you're dealing with complementary angles immediately gave you one of your two equations. Now, there are some problems that you've dealt with before that are now going to be a little bit easier to deal with, and those are going to be your mixture problems, which include, of course, your money problems, and also your distance, rate, and time problems. Now let's look at the ones that are going to change the most, and those are your mixture problems, which of course includes money problems. Let's look at an actual money example. Let's say you're going to invest $10,000. That $10,000 is going to be split up between two investments. One paying 5%, one paying 6%. In the end, you come out with $540 in interest. And you need to know how much has been invested in each account. Now, when we set up our money and our mixture problems, there's two basic formula types, two basic equation types we're going to use. One formula is going to deal with the amount that you have. The other formula is going to be dealing more with value. So let's look at specifically what I'm talking about with these two formulas. First of all, amount. The amount of money you had was $10,000. It's being split two ways. So our first equation will be x plus y equaling 10,000. The second equation deals with value. Value is going to be either, in some cases, a dollar figure, in a lot of cases, percentages. So the first investment was a 5%. The second investment was a 6%. And remember, percent means decimal times variable, decimal times variable. This came out to be $540. So this is the way that the money problem could be set up using two equations and two variables. Now this one, I'm not going to solve all of these because our emphasis right now should be the setup. If you want to know how to solve them, then you're going to use either substitution or elimination. Okay, I'll solve this first one, but from here on out we'll just set them up and leave the solving to the student. I'm going to use substitution. So I will step aside here and solve for the x variable. And x is going to be equal to 10,000 minus y. Then I'm going to come up here and substitute 0.05 times that 10,000 minus y. I've substituted in for x and leave everything else as it was. Now I need to multiply. So let's see if the calculator can help us distribute this 0.05. We're going to take 0.05 times 10,000, and that gives us 500 minus 0.05y plus 0.06y equaling 540, combining like terms, 0.01y plus 500 equals 540. Subtract off the 500. Get 0.01y equaling 40. Now I need to divide by the 0.01. So on the calculator, I'm going to take the 40, divide by the 0.01, and that becomes a 4,000. So y is $4,000. That means the money was split 4,000 and 6,000. 6,000 in at 5%, and the 4,000 in at the 6%. So the problem, the mixture problems and money problems actually become just a little bit easier if you're allowed to use two equations and two variables. Let's take a look at another mixture problem. Let's say you had a family reunion at an amusement park. Adult tickets cost $40. $440. That would be a pretty pricey park. The children, their tickets cost $30. Well, let's say 27 tickets were sold for a grand total of $930. We need to know how many adult tickets were sold and how many child tickets were sold. First of all, amount. The amount's going to be adult tickets plus children tickets equaling 27 tickets. Now for value. It's going to be $40 times the number of adults plus $30 times the number of children equaling the grand total $930. And as promised before, I'm going to leave it for you to solve But that is the way the setup will go. Let's look at one more example of setting up a mixture problem. Let's go back to the pharmacy. Let's say the pharmacist needs 1,000 milliliters of a 10% solution. On hand, there is only a 5% and a 25%. So, how do we mix? All right, again, let's look at the amount. We're going to use X milliliters of 5% plus Y milliliters of 25% to give you your 1,000. Now for value, and again, not value in a monetary sense, but in this particular example, in a percentage sense, value 0.05x plus 0.25y is going to equal the total 1,000 times the 0.10, which is going to be your final concentration on your mixture. So again, amount and value, and the problems with mixture and money become a little bit easier. Now, one other type of problem that you've seen before, that you're going to see more of, is going to be the distance, rate, and time problems. Well, distance, rate, and time problems can be done using systems of equations, but it's really not the easiest way to do it. For distance, rate, and time problems, I suggest that you continue to use the box where you organize the distance, rate, and time information, and continue to do those problems in pretty much the same fashion. Let's review one of those problems. Let's say that two trains are 560 miles apart and traveling towards each other. Alright, so let's go ahead and set up our box, because we know we've got two trains, and each one has a distance, a rate, and a time. Alright, one train is traveling 6 miles per hour faster than the other. So if we had a slow train and a fast train, then this would be R, and this would be an R plus 6. The trains would pass each other in 4 hours, it says, so we'll give a time of 4 for each. Multiplying, we're going to have a 4R for distance, and a 4R plus a 24 when I distribute. Again, not needing two equations, not needing two variables, because the box organizes this information so well. Since they're heading towards each other, we're going to take their two distances, add them together, and set it equal to the 560 miles that they're going to travel. 4 and 4 is an 8R. We're going to take 560, subtract off the 24, that's 536. Now I need to divide by 8. So go ahead and let the calculator help us with that. Divide by 8, and we get 67. So the trains are going to go 67 and 73 because the faster one was 6 faster. So with the distance, rate, and time problems, setting up two equations really isn't necessary and isn't really any easier. Now there's a new type of problem we're going to see once we're able to use two equations and two variables. Whenever you have a boat traveling through water or an airplane traveling through the air, the current or the wind can have a very predictable effect on that boat or that airplane. Let's say we had a boat that was capable of traveling 10 miles per hour. If that boat is going downstream and the current is moving at 3 miles per hour, since the current is moving with the boat, that's going to give you a net effect of 13 miles per hour. But the same exact boat in the same stream, if it was to head upstream, then that 10 miles per hour would have the 3 miles per hour taken from it, and in the end it would only be capable of traveling 7 miles per hour. So, with a boat or an airplane, downstream, upstream is going to give you two equations, or with the wind, against the wind is going to give you your two equations. Let's look at an example. Let's say that Mike is kayaking, and he can travel 4.7 miles per hour with the current. That means that Mike's speed plus current equals 4.7. And it also says he can travel 3.4 miles per hour against the current. So that'd be Mike minus current equaling 3.4. So this is going to be the basic setup for any problem where wind speed or current get involved. The speed of the boat or the plane plus current gives you one equation, and the speed of the boat or the plane minus current gives you the second one. And most of these are going to be very easy to work with a addition method. I'm going to add. I get a 2m, the c's cancel, equaling an 8.1, dividing by 2. Let's see what that's going to be with the calculator's help. 8.1 divided by 2 is a 4.05. So Mike can paddle at 4.05 miles per hour, and I could plug that easily back in and find the current. I'll subtract off the 4.05. That tells me the current is going to be 4.7 minus that answer, which is a 0.65 miles per hour. So that's the way you'll handle all problems involving current and airspeed.